Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will introduce two very important functions. One, the cumulative distribution function, or CDF, and the probability density function, also known as PDF. These functions are very important when dealing with continuous random variables. Let's begin. The plan is the following. First, we're going to introduce CDFs using an example. Okay? Since you guys have a lot of experience at this point with discrete random variables, we're going to start there. Okay? Then, from that example, we will motivate the definition and properties of CDF and PDF for continuous random variables. Okay, let me show you our example, our particular problem. So as I said, we are going to start with a discrete random variable because you guys have a lot of experience at this point with those. Okay, so we have a random variable x and we have its distribution, meaning the list of possible values for this random variable along with the corresponding probabilities. And we want to find an expression for this guy, capital F at x, a new function that we are defining as the probability that the random variable x is less than or equal to lowercase x. Okay? And once we have that expression, we would like to provide a graphical representation of that function. Okay, so let's begin. Solution. So we will have to proceed, case by case. Okay. So this function, this new function, capital F at x, right, must be defined from negative infinity to infinity. Okay, so let's take into account all the possibilities that we have. So first, case number one. Let me use a different letter, if you will, to avoid confusions. If k is less than 1, okay, then what we want to do is finding f evaluated at k, and we know that we defined that guy as the probability that the random variable is less than or equal to that k. Okay? That's just by definition. Now let's think about this. If k is, for instance, 0, we would like to know what's the probability that the random variable is less than or equal to 0. We could think about this random variable like a four-sided die. Okay? Probability of rolling a 1, 0.4, probability of rolling a 2, 0.3, probability of rolling a 3, 0.2, and probability of rolling a 4, 0.1. Right? So if someone asked you, hey, what's the probability of rolling something that is less than or equal to, say, -1, then you would go, the probability of rolling a -1 or less, a value that is less than or equal to -1 is 0, because these are the possible outcomes. Make sense? So that would be true for any value k that is less than 1, right? How about the probability of rolling something that is less than or equal to 0? Again, 0. How about the probability of rolling something that is less than or equal to -2? 0. Can you see it? Okay, so that's our first case. Case 1. Now let's move on. Let's talk about the next case. Now, how about we take a value that includes 1 and is less than 2, okay? So if we have a k that lives between 1 and 2, including 1. So let's see. Again, let's use the definition of the function capital F. So f at k is by definition the probability that the random variable x is less than or equal to that particular k, right? So again, let's think in terms of a particular case. So say that k was 1.5, okay? The probability of rolling something that is less than or equal to 1.5, that would be what? Oh, that would be the probability that x is less than or equal to 1, right? If k was 1.5, hey, that's the same as the probability of x being less than or equal to 1.5, right? Because we don't have a 1.5, right? It would be the same if k was 1.7 or 1.8, right? Probability of x being less than or equal to 1.8 is the same as the probability of x being less than or equal to 1, right? And that probability happens to be just 0.4. Make sense? Okay. Next case. Now, as you can imagine, the next case would be taking a number that lives between 2 and 3, including 2. Okay? Let me copy paste this. Our next case. Now 2 and 3. Again, we will use the definition. So uppercase f at k is just the probability that the random variable x is less than or equal to k. So for instance, if we had that k was 2.2, the probability that x is less than or equal to 2.2 is the probability that x is equal to 1 plus the probability that x is equal to 2. Right? Guys agree? Make sense? And that, this case, let's go back to our table, would be 0.4 plus 0.3. Okay, so 0.4 plus 0.3 that happens to be 0.7. 0.7. Next case. Now let's take a value k that lives between 3 and 4. Between 3 and 4. In that case, again, we are going to be using the definition of uppercase F. So if we had, say, 3.7, what's the probability of rolling something that is less than or equal to 3.7? It's the probability of rolling a1, or rolling a2, or rolling a3. So let me copy paste these, and I'm going to be adding the other one. Then I'm going to need the information coming from our table. So it's going to be 0.4, 0.3, and 0.2. So 0.4, 0.3, and 0.2, that will be just 0.9, right? We're almost there, because as we said, we would like to define this function, uppercase F, for any number between negative infinity to infinity. So last case, case 5. If k, right, happens to be a number between 4 and infinity, okay? So again, let's use the definition of uppercase F. And again, if, say for instance, k was 6, we have a 4-sided die. What's the probability of rolling something that is less than or equal to 6? It's 1. You guys agree? Because we know that the highest this can be is 4. So the probability of rolling something that is less than or equal to 6, for instance, that happens for sure, right? But let's be very specific. It would be just the sum of all these probabilities. So it would be the sum of all these plus the other one, 0.1, that was the other one, and that would be 1. Okay? Make sense? Okay, so we're done with part A. We have defined that function, uppercase F, for any number between negative infinity to infinity. All those cases are here. Okay? Now let's try and do part B. We would like to have a graphical representation of this new function, capital F. Okay? Let's use R to do that. Here we go. First, let's define a vector x. Okay, let me remind you that we have the possible values for a random variable being 1, 2, 3, and 4. So we have 1, 2, 3 and 4. Now let me also create a vector P that contains these probabilities. So using that function C concatenate, I'm going to be doing that. We have done that before. We have used that function before. So we have X, we have the corresponding probabilities for each of those values of the random variable. Okay. Now let me introduce, let me show you a new command in R that is going to help us find what we want. We can see from what we did here that, for instance, f at k, right, is going to do the sum of all the values less than or equal to k. So that's why this new function, this capital F function, it's called the cumulative distribution function, right? Because it's doing the sum up to that point. Okay. So there is a sum. There is a function called cumulative sum in R that is going to help you do that, right? Let me show you. If we use that function, cumulative sum of P, up to this point we have 0.4, up to this point we have 0.7, up to this point we have 0.9, up to this point we have 1. Make sense? Okay. So let me save those here. I'm going to call those capital F. Okay. And now let's make that graph. Okay. So note something interesting. So you have that if k is less than 1, you have 0. Okay, so you have a flat line if you have a k that is less than 1. Okay, 0. Then once you hit k equals 1, you're going to have another flat line that looks like this, 0.4. You are going to have that value for any k that lives between 1 and less than 2. So once you have up to k equals 1, you go 0, 0, 0, you hit 1 and then 0.4. And you will have that value 0.4 for any number k between 1 and 2. Once you hit 2, you go to 0.7, and again it's going to be constant, 0.7 for any number between 2 and 3. So what you will have is a staircase, a step function. So it turns out that R has a built-in function to create step functions. Let me show you. So let's save that in an object called sFun. So step fun, as in step function of x, and then what I want you to see is that we would like to add this guy 0 and f. Okay, let me show you what I'm doing there with that CF, right? I'm just adding 0 to that vector that we already had. Okay, because we know, right, from the first case we should have that f is 0. Okay, that's why we're adding that guy. Now let's define our step function, and this is the built-in function in R, the command that will create that step function for you. Okay, so x will be unchanged, but we want to add that 0 to the values of the function f. Okay, so now let's just use that command, plot. Okay, we want to plot our step function. We have a few options here, a few parameters. So verticals, false, PCH equals 19. What that is going to do is telling R that I want solid circles. Okay, and just to make it look nice, I would like to add some labels. Y lab stands for the label for the vertical axis. So what I want there is just something that looks like this, an expression. Oh, I don't want this, so it would be expression, because I want something fancy. What I want is the probability that x is less than or equal to x. Okay, I think that should work. And then something else. I would like to add a main title. I want to say that this is the CDF of my random variable x. Okay, let's see. Let's hope this works. Yeah, it does. So that's why I used that PCH equals 19. Then we are going to have those solid circles here, right? And let's see. I want you to see clearly that that graph corresponds to the function we found. Okay, so we have that if k is less than 1, then f at k is 0, right? If k is less than 1, that function is 0, right? Then between 1 and 2, including 1, we have 0.4, right? Between 1, including 1 and 2, we have 0.4. As soon as we hit 2, right, we jump. We jump to 0.7. Okay, so we have 0.7, right? And then we remain in that level up to 3. Once we hit 3, we have 0.9, and once we hit 4, we have 1. Make sense? So it's a step function. Got it? Okay. Now, what I'm going to do is I'm going to refer to our lecture notes. I'm going to show you a couple of definitions and properties of this CDF. Okay, so just give me a sec. I'll be right back. Okay, I'm back. As you can see, right, we have a definition from our textbook. This is in our lecture notes corresponding to chapter 4, right? And we have the definition of the distribution function, or CDF, cumulative distribution function. Note that by distribution function, right, we mean the CDF. We're not saying the distribution of y. Okay? So, but I will try to be very explicit, very specific when we want the CDF. Okay? Okay. So anyway, that's the way the CDF is defined. It's, you know, just the probability that you have up to a certain point. Okay? And in the case of a discrete random variable, it would be the sum of all the probabilities up to that point. Okay? As we saw in our example. Okay? Now, a theorem. We're not going to show that theorem, but that's why we spent some time with this example to gain some intuition behind this, behind the properties of a CDF. So the CDF, right, will have these properties. The limit as y goes to negative infinity of uppercase F, the CDF of y, is 0. Let's go back to our example. Right? If you go way to the left, right, as y goes to negative infinity, that's a behavior that you will observe in a legit CDF, that the CDF will be 0. Okay? That's one. Property number 2. If you go way to the right, as y goes to infinity, the value of the CDF of uppercase F will tend to be 1. Okay? Something like this, right? So a CDF is a function that always, the values of a CDF are always between 0 and 1. Okay? And then f of y is, and be very careful about this, that's why we use this word, non-decreasing. One may be tempted to say that it's increasing, but then our mathematician friends would go, hey, 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 here we don't have an increasing behavior, right? So that's why we're being very explicit, non-decreasing, but that's the kind of behavior that you will see. Okay? So, and we know, right, from math courses that a function will be non-decreasing if y is less than if y1 is less than y2. That means that the function evaluated at y1 is going to be less than or equal than the function evaluated at y2. Okay? Okay. Now, we said that now in this chapter 4 we are going to be interested in studying continuous random variables. Okay? So it turns out that the definition of a continuous random variable is related to the behavior of its CDF. Okay? So we're going to say that a random variable y with CDF f, uppercase F, is going to be continuous if the CDF is continuous. Okay? That's the definition of a continuous random variable. Okay? Now, we also at the beginning mentioned that we were going to introduce another function, the PDF, the probability density function. And again, that function, the PDF, is related to the CDF, the cumulative distribution function. Okay? So to obtain the PDF of a continuous random variable, all you have to do is take the derivative of the cumulative distribution function with respect to in this case we're using y as the variable, so just take the derivative with respect to y of the CDF. That is going to give you the PDF, the probability density function. Okay, so that's what we wanted to do in this video, right? Introduce those two important functions in the study of continuous random variables, the CDF and the PDF. Well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.